Welcome! This video is on conditional probability, the probability of A given an event B. And we'll start with a very basic talking Elmo example. And you want to know if advertising is related to people buying a product. And so we have data on whether they bought a talking Elmo doll. This is what a talking Elmo doll looks like, it talks. And didn't buy a talking Elmo doll. And we have data on whether they saw the ad, did not see the ad. Here's our joint probability table. Is this a legal table? Yes, it is. Everything adds up to 1. And what we have here, those are called the marginal probabilities. So 30% of our group bought, 70% did not buy, 50% saw the ad on TV, and 50% did not see the ad on TV. Marginal probabilities are also called unconditional probabilities. They're the overall probabilities. They're not conditioned on anything. From the table, what's the probability that someone bought an Elmo doll? Bought, we just said, that's 30%. So we'll say 30% right there. Is advertising effective? And what we want to discover is, given you saw the ad, are you more likely to buy the doll? So ideal, is it higher than 30%? Is seeing the ad related to buying the doll? So we're looking for this conditional probability, the probability you bought Elmo given you saw the ad. So that bar means given. It's called a conditional probability. So what's the probability you bought an Elmo doll given you saw the ad? We want to know if advertising is effective. If this probability were, say, above 30%, you might say advertising is effective. We won't say causing. We can't say advertising causes you to buy the doll. We can't make a causal statement. We might say advertising is effective. That vertical bar is called the conditional probability bar, and we say given. So probability bought Elmo given you saw an ad on TV. The definition of conditional probability, probability of A given B for events A and B, is simply out of all the times B happened, how often does A also happen? So we call this the joint probability divided by the marginal probability. Out of all the times B happens, how often does A also happen? So we can compute these. Probability you bought Elmo given you saw the ad. Well, what goes on the bottom? That's going to be the probability you saw the ad, which is 0.5. What's the probability you bought Elmo and you saw the ad? Bought Elmo and is 0.2. That's 0.2. This is going to be 0.4. What's the probability you bought Elmo given you did not see the ad? Well, I know that's 0.5 on the bottom. What's the probability you bought Elmo and did not see the ad? Bought and did, that's 0.1. 0.1, and that equals 0.2. So remember, the overall probability that you bought, all right, so big with my finger, is 0.3. Would you say advertising is not working or working? Given you saw the ad, you're more likely to buy the doll. So we'd say advertising is indeed working. One way to think of this is think of an auditorium full of people. And you say, how many people in here bought a doll? 30% say we bought the doll. Now you say, okay, everyone who saw the ad stay, everyone else leave. So you have a room full of people who just saw the ad. Out of you who saw the ad, how many bought the doll? That would be 40%. If you did the same exercise where you just had the people who did not see the ad stay, you say how many bought the doll, that would be 20%. So there's a difference. Seems to be some sort of relationship between seeing the doll and seeing the ad and buying the doll. As an example, giving you like Sprite, what's the probability you're a male? So here we have this. We might as well make the conditionals, the marginals 0.55, 0.45, 0.62, 0.38. The probability of male given Sprite is going to be the probability of male and Sprite, 0.15 over the probability of Sprite, which is 0.38. And we can figure that out on a calculator. But again, calculating conditional probabilities is very straightforward. What do we do with conditional probabilities? Well, we often want to know, is there a relationship between A and B? And we say A and B are independent if the probability of A given B equals the probability of A, or the probability of B given A equals probability of B. If that equality does not hold, we say A and B are dependent. So basically what this is saying is, given that B happened, does that affect the probability of A? If given that B happened, the probability of A is not affected, does not change, we would say A and B are independent. If the probability does change, we would say A and B are dependent. Example, what's the probability you'll draw a king given you've already drawn a red card? Well, the probability to draw a king, there are 4 kings, there are 52 cards in the deck, it's 4 out of 52. Given it's a red card, it turns out the probability of king and red card, half the cards are red and half the cards are black, and there are 4 kings, but the math works out to be exactly the same. So knowing you draw a red card gives you no new information about drawing a king. And that's because, again, they're evenly split. But we'd say drawing a king and drawing a red card are independent. They're not related to each other. However, in the Talking Elmo example, probability you bought overall is 30%. Given you saw the ad, the probability you bought is 40%. They're not the same. They don't equal each other. So we would say A and B are dependent. You could even say they're positively dependent in that knowing that seeing the ad happened, you're more likely to buy the doll. But all we would say is they are dependent. Buying a doll depends on whether or not you saw the commercial on TV. As another example, here's Apple and Gap, and these are on a daily basis. Do they rise? Do they decline? And are they unchanged? Are they independent or dependent? Now, you can go anywhere you want. That 0 is sort of looking at me, and so I want to work at that symbol. The probability that Gap is unchanged, sorry, I want to write unchanged, given Apple is unchanged, equals the probability Gap is unchanged. Okay, this looks like a 5-year-old wrote this. So we write, well, I meant to write equal there, question mark. I don't know if it's equal. I'm really messing that up. So what's the probability Gap is unchanged given Apple's unchanged? Well, we can compute that with the definition of conditional probability. We know it's going to be in the numerator, Gap unchanged and Apple unchanged, which is 0. So this is 0. However, what's the probability Gap is unchanged? That's 0.007. And we're looking for straight equality right now. So we would say that they're not independent, they're dependent. If you have equality here, if A given B equals A are equal, you'd say they are independent. If not, they're dependent. We don't have equality here, you would say they're dependent events. Actually makes sense because they're both big companies in the stock market. If one goes up, the other should go up. One goes down, the other goes down. So you'd think they're dependent, and we just said they are actually dependent. Now, independence is a very strong assumption. And that's because if things are independent, probabilities multiply, as we'll show in a minute. But probabilities usually don't multiply because things in general are not independent. The thing is that you get a really nice result. If A and B are independent, A given B equals probability of A. And so if you work through this, you get this result that says if they're independent and you want the joint probability, you multiply the marginals together. This is only true, though, if they're independent. This is a big deal, though, because we say life is a huge joint probability. Like, what's the probability you get a good job and you get a nice car and you move out of your parents' basement and something else and something else and something else. In general, we want to know a huge joint probability. We want to know what's the probability A and B and C and D and E and F and all that stuff happen at the exact same time. In the stock market, what's the probability of oil and gold and real estate and Bitcoin and something else? What's the probability they all do these different things? Well, if I can multiply them individually together, it's easy to find the answer. But in general, you can't. Life is a huge joint probability, but we can't approximate it by just multiplying these things together unless we assume these events are all independent. So it's called the multiplication rule. It's very nice. If events are independent and you want the joint probability, you multiply the marginal probabilities together. As an example, you have 2 spinners that are independent. What's the probability you spin an even number and a vowel? You just multiply the probabilities together. Very straightforward. It works for any number of events if you're told they're all independent. If you have a bunch of events that are all independent, the probability of E1 and E2 and E3 and whatever is just the multiplication, the product of the individual probabilities. As an example, the probability of a randomly selected female age 60 will survive the year is 99.186. What's the probability that 4 randomly selected 6-year-old females will survive the year? Well, the probability all 4 survive is the first and the second, the third, and the fourth survive. And because of independence, we just multiply those probabilities together. So independence buys you a lot. showing you an example at one time of independence and the complement rule. Go through this nice little example here. This is a real-life example. During the 1979 baseball season, Pete Rose of the Cincinnati Reds set a National League record by hitting safely in 44 consecutive games. Now, hitting safely means you make at least one hit. At least one hit. 1 hit, 2 hits, 3 hits. You make at least one. Now, to make life easy, we're going to assume that Rose is a 300 hitter. And if you're inside a hitting streak, that's going to go up and up and up, of course, but we're going to assume he's a 300 hitter. That means anytime he's at bat, the probability he makes a hit is 0.3. And we're going to assume he comes to bat 4 times each game. This makes our life a lot easier. If each at-bat is assumed to be an independent event, another strong assumption possibly, what probability might reasonably be associated with a hitting streak of that length? What's the probability he hits safely in 44 consecutive games? Now, this is good to see because there's several steps here, and we break down this problem into nice little bite-sized chunks. We want A sub I to denote the event Rose hit safely in the ith game. The probability Rose hit safely in 44 consecutive games is he hit safely in game 1 and game 2 and game 3 and game 44. But this huge joint probability can be written as the product of these marginal probabilities. Why? Independence. We now need to find probability of A1. The probability of A1 is the same as A2, A3, A4, A5 because we assume the setup is the same for each game. We assume he comes to bat 4 times, he's a 300 hitter. So what's the probability of A1? The probability of A1 is the probability he hit safely in game 1. And that's actually a little bit of a pain to find because he could hit once or twice or 3 or 4. It would all hit at least once. He hits safely means he hits at least once. Well, the complement is 1 minus the probability he does not hit safely, which is 1 minus the probability Rose makes 4 outs, which is 1 minus 0.7 to the 4. Why? The probability makes a hit's 0.3, the probability makes an out's 0.7, the probability makes 4 outs is 0.7 to the 4th. So then you get 0.76 for that. Then the probability he hits safely in 44 games is just going to be 0.76 to the 44, a very, very small probability. We always tell people this is a great slide to go over because it looks at the complement rule, it looks at independence, just makes you think about several things at once. So this is a great slide to review. Now, as we said, it's an important warning. A and B is called a joint probability. If you add more, probability of A and B and C and D, it's still a joint probability. In general, joint probabilities are hard to find. If you are told the events are independent, score. You can find a joint probability by multiplying the marginals together. However, you have to be told that. You have to somehow know the events are independent. Don't just start multiplying probabilities together to find a joint probability unless you're told the events are independent. Hope that helped a little bit and that you're having a great day, and we'll talk to you soon.